In this video, I wanted to talk about graph coloring. Graph coloring is a very interesting topic that overlaps with mathematics and computer science and has a lot of applications. So you're given a graph, and you would like to assign a color to every vertex. This is called a coloring. So it's just an assignment of a color to every vertex. Now a valid coloring is a coloring where no two adjacent vertices receive the same color. Okay, so for example, in this graph, I could color this vertex red. That forces me to color this vertex, say, green. Now I can use red again. I'm trying to create a valid coloring. If I colored this vertex green, it would be a coloring, but it wouldn't be valid because it would be connected to this green vertex. So I'll color it red. And okay, I'll color this vertex green. And now I'm in trouble. If I color either this red or green, it's not going to be validly colored. Fortunately, I have a blue marker here, so I'm going to color that vertex blue. Okay, so we used 3 colors to color the graph. This implies that the graph that I drew is called 3 colorable. It turns out that for this particular graph, so for this graph, we must use at least 3 colors. Why is that? You'll see how to identify that property in an upcoming lecture. But for right now, let me just tell you, or take it on faith, that this graph does indeed need at least 3 colors. We were able to color it with 3 colors. This implies that the chromatic number of this graph G is 3. What is the chromatic number? It's the smallest number of colors you need to validly color the graph. So in this case, the chromatic number is 3 because we could color it with 3 colors, and we need at least 3 colors. So the chromatic number of this particular graph is 3. One of the most common applications of coloring is scheduling. For example, let's assume that we have, well, we obviously have many students in class, but let's let one vertex correspond to different courses in the CS curriculum. So here's 313K, here's 336, here's 337, 341, 395, and so on and so forth. So we could have one vertex for every course, and then we could put an edge between 2 courses if there's a student in both of those courses. So if there's a student that's taking both 337 and 336 in the same semester, we put an edge. If there's a student taking 395 and 341 in the same semester, we put an edge, and so on and so forth. So So now remember, we're not going to have multiple edges. But this edge sort of means that there's a potential conflict. We want to schedule all these courses so that there are no conflicts. So, for example, since there's an edge between 337 and 336, we know that we can't schedule 337 at 1 p.m. and 336 at 1 p.m. because it'll conflict for this student. It's okay to schedule 336 at 1 p.m. and 341 at 1 p.m. because there are no students taking both 336 and 341. Again, if we scheduled 341 at 2 p.m. and 395 at 2 p.m., that would be no good because it would create a conflict for these students. But we'd like to schedule all of these courses using the smallest number of time slots as possible. So we could have one color for each time slot during the day. So for example, we could have the 1 p.m. color, we could have the 2 p.m. color, and we could have the 8 a.m. color. I don't know if they schedule classes that early. But you can see the problem now. If we want to come up with a schedule for these courses such that there are no conflicts, then what we need is a coloring of these vertices. We need to assign a time or a color to each one of these vertices so that no two vertices get assigned the same color. That is, if we use the 2 p.m. color, say I color this 2 p.m. and I color 341 2 p.m., that's okay because these two vertices are not adjacent. I can't color 313k now with the 2 p.m. color because it's connected to 336, so I'd have to use, say, the 1 p.m. color. But given a list of courses and all the students taking the courses, you have the problem: find a schedule with no conflicts using the fewest number of time slots. This is exactly equivalent to find a coloring, a valid coloring of G using the minimum number of colors. So you can see that this is a pretty useful and important problem, and it arises in many, many, many other applications. Unfortunately, in general, if you give me a graph and ask me to find a coloring that minimizes the number of colors and produces a valid coloring, it turns out to be one of these famously hard NP-complete problems. Still, we can prove lots of interesting things about graph coloring and come up with many interesting algorithms that we'll see as we proceed through the graph theory unit.